Welcome everyone, Mr. Weiser here. This lesson is going to be about normal distributions. Let's get started. Our first task is to be able to determine if a distribution is approximately normal. And obviously we can use the eye test to see if some of them are going to pass or not. For instance, here, this is skewed to the right, and this is bimodal. So you're not going to have that classic normal shape that looks like this. So it kind of fails that by the eye test. But they're not always going to have the eye test. Sometimes in this scenario, if you're just trying to determine if it's going to be approximately normal, you could make the case for this one by looking at it that it might fit that test, maybe if this little outlier wasn't there, if that even is an outlier. So to investigate, we really want to use the empirical rule, the 68, 95, 99.7 rule. We'll need to have all the data for that. So this is that age of US presidents when they first took office. The numbers are all there and they're rounded to the nearest hundredth of a year when they took office from smallest to largest. And the question is going to ask, does this distribution give an approximately normal distribution? It doesn't say exactly normal, just approximately. Give evidence to justify your answer. So the first thing we want to do is we want to look at the mean and the standard deviation. And the mean and the standard deviation are going to be provided here. You don't have to get them yourself. So 55.97 and 7.347. The next thing you're going to do is you're going to count out one standard deviation below and above the mean. So you're going to ask the question, what percent of the data points are within one standard deviation? So subtract the mean in the standard deviation and add the mean in the standard deviation. Use your calculator and you'll get about 48.534 and 63.408. So what you're going to do with that is you're going to go to your data points over here. You're going to count, find where the mean is first. So 55.971 will be somewhere right there. And you're going to count all the way until you see all the values that are between 48.534 and 63.408. So when you do that in this case, you're going to get 32 values. We don't want to use 48.28 because that's below. So 49.29 is the first number above this one, and 62.27 is the last number before 63.4. So there's 32 numbers there. So you're going to take that 32 since there's 46 values altogether. You'll take that and divide by 46. That's going to give you 0.6956. So that's roughly about 69.6% of the values. It's not too far off from 68. So then we do the same thing with two standard deviations. We go two standard deviations out from the mean, subtract 2 times the standard deviation, and add 2 times the standard deviation from the mean. You're going to get about 41.277 to 70.665. You go back up to your data and you see how many fall between those numbers. So it looks like all of these up here will be between 41.277 and these three, but once I hit 78.17, that's too high. So it looks like we have all but that last one, which is going to give you 45 values. 45 divided by 46 is about 97.8, not too far off from this 95. And so lastly, we'll go 3 standard deviations out, do the same thing, do the math, use your calculator. In this case here, we still have 78.17, a little bit outside, just barely. So again, that's going to be 45 divided by 46, which is about 97.8%. Now, remember, we're not trying to see if it's exactly normal. We're just trying to see if it's approximately normal. So we're going to look at these 3 percentages. And we want to compare them to the empirical rule, 68, 95, and 99.7. And to be fair, they're not really too far off. So in this case here, since they're all fairly close, within a couple percentage points either way, I would say that the data mostly follows the empirical rule. We can approximate a normal distribution with this data. Here's to check your understanding. At the right are a dot plot and numerical summaries for data on caloric or calories per serving in 77 brands of breakfast cereal. The graph is roughly symmetric, single-peaked, and somewhat bell-shaped. Is this distribution approximately normal? Give appropriate evidence to justify your answer. You're going to want to head and go and pause the video on this one so you can try this one on your own. All right, I'm going to go ahead and reveal the solution in 3, 2, 1. So first, within one standard deviation, you're going to get roughly 63 data points. There are 77 data points here. So 63 divided by 77 is 81 or 0.818, which is 81.8%. That's pretty high. That's a lot higher than 68%. So we already know it's not really going to follow a normal distribution here. We'll go ahead and do the other ones. If I go out two standard deviations, I'm going to get about 92.2%. That's fine. And then three standard deviations is all of them, which is close to 99.7. It's 100%. So the last two are okay. It's just that first one, that 81%, that's too much. Most of that's concentrated within one standard deviation. So it's not going to be considered a normal distribution in this case. So now let's talk about how to compute values in a normal distribution, besides just using the empirical rule. We want to make some estimates. So you might remember this example from the previous lesson we did. This is the Iowa Test of Basic Skills. And in this case here, the mean of this test for the grade 6 level students who took it is 6.84 with a standard deviation of 1.55. What we want to know is not the percentage at or below a certain value that's right on a standard deviation count, but somewhere between. So what I want you guys to do is estimate those percentages. What percent do you think is shaded below 6 in this distribution? Now that you've got that, let's see if you can estimate what's above 9. Just jot your estimates down. Don't worry if they're going to be off. You can always change them. What about between those two, between 6 and 9? Finally, can you estimate the value at the 90th percentile? So in other words, when 90% of this area is shaded to the left, what would be that value in this distribution? So we can check this using technology. We'll check this on Stapplet.com. So if you go to Stapplet.com, go to normal distributions, and let's plot in our values. So it's 6.84, and the number here was 1.55. Oh, that's binomial. All right, here we go. So we want to calculate the boundary, and we'll say to the left of 6. And you may have estimated, hopefully somewhere close to that, 29.39%. And then to the left of 9, or to the right of 9, rather, that's going to be about 8.17%. Between two values, so between 6 and 9, you get 62.43%. And then we want to estimate, given the area, so let's see, outside of a region, to the right, to the left. So we're going to go up here, calculate a value corresponding to an area. And that area was the 90th percentile, so left tail. And looks like that gives you a value of about 8.826. So we're not going to have Stapled on a test in this class or on an exam. So we have to learn how to calculate this in a couple different ways. The first way we'll use is using our table A. You're going to be provided a table of normal calculations. And these calculations are going to be percentiles below, so values below a certain number on a Z standardized normal distribution. So in order for this to work using the table, you have to get Z scores for all of your data or for all of your values. So in this scenario here, we'll have to get a Z score. So if I were trying to go below 6, we have to figure out what is the Z score at 6, knowing that the mean is 6.84 and the standard deviation is 1.55. So to do that, remember Z score is value minus mean divided by standard deviation. So you'll do your 6 minus 6.84 divided by 1.55, and you'll get a Z score of negative 0.54. Now remember, that means that it's 0.54 standard deviations below the mean. Now you're going to have a table of normal calculations. This would be table A. Let me blow that up a little bit. And on table A, what you're provided is all these percentiles, and the z-scores are listed out here. So you have the first decimal place for the z-score, followed by the second decimal place. So if you look at negative 0.54, you can actually go to the zeros, negative 0.5, and then you're going to go over to the 4 in the hundredths place. So negative 0.5, and if you follow that, it's going to be right here. So those are going to line up in these two places, this column and this row. And this overlap, this 0.2946, that'll be your probability below that point. So the probability of being at below 6 or below a z-score of negative 0.54 is about 29.46%. You can go above. So if I want to go above 9, then I'm going to get that z-score for 9. And we'll do 9 minus 6.84 divided by 1.55. And you get a z-score of 1.39. So you want to go into the positives on the table here. You're going to want to go to 1.39. 9 is all the way over here. And you want to find that percentile. Now remember, these numbers are below a z-score. So that 0.9177, that's not going to match up the shaded area. It's going to match up the complement of that. So 1 minus that. So what you're going to do in this case here is you're trying to find the value less than or greater than rather, but you on the table you're getting the value less than. So 0.9177 is less than 1.39. We want to know the probability of Z being greater than that. So we're going to subtract that from 1 since this distribution would all add to 100% of your data, 1. That's going to give you about 8.23%. If I want to go between two numbers, then I'm going to do the two percentiles, and we got those before, and we're going to subtract them. So if you subtract those two numbers, you get about 62.31%. So that's not too bad to do. And finally, if I want to know a specific value given the area, we'll have to work backwards. So what we'll do in this case here is we're actually going to look in here and find the percentile, and then go out and find your z-score from there. So what we'll do is on the table, let's try to find the 90th percentile, or the number that's as close to 0.90 as possible. And when you go through that, you're going to see a lot of numbers that are close, like 0.9032, 0.9015, 0.8997. And it looks like these two numbers are the closest, but the one that's the most closest is 0.8997. That's just 3 thousandths shy of being 0.9. So we'll use that number. We'll go out to the edge, so the column in the row, and we'll see our z-score of 1.28. Now that we have our z-score, we'll set up it in the formula. We'll plug in our standard deviation and our mean, and we'll work backwards to solve for x. So we're going to want to multiply that 1.55 up here, and then we're going to add the 6.84. So 1.28 times 1.55 plus 6.84 will give you your value. And you get about 8.8824. So remember on the original graph here, 8.824 would be right here. Notice that it's over one standard deviation above the mean. And remember our z-score was 1.28, so that does track. You can also use your calculator to get all this stuff. So I'll show you how to do that in the first example here. So you're going to use something called normal CDF or table A. I prefer to use the calculator. So let's look at this example. We want to calculate the area from a normal distribution. And in this case here, I'm going to show you how to use your calculator to do that. Many studies on automobile safety suggest that when automobile drivers must make emergency stops, the stopping distances follow an approximately normal distribution. Suppose that for one model of car traveling 62 miles per hour under typical conditions on dry pavement, the mean stopping distance, mu, equals 155 feet with a standard deviation of sigma equals 3 feet. In your book, it doesn't have the number, so it should be 3 feet. Dontrell is driving one of these cars at 62 miles per hour and spots an accident 160 feet ahead that requires an emergency stop. Is Dontrell likely to be able to stop the car in less than 160 feet? Justify your answer. That's a lot to pursue, so let's go through and see if we can mark a few things that we're given. So in this case here, one thing that I noticed, I'm given a mean and a standard deviation. The 62 is really irrelevant information because we're just talking about cars that are traveling 62 miles per hour. So I don't really need that right now. So I'm going to go ahead and cross that out. We do have an accident that's 160 feet ahead, and we want to know the probability that Dontrell is likely to be able to stop the car in less than 160. So that's an important thing in this case. So what I want to do first is I want to visualize a sketch. And on these problems, you should draw a sketch. So always sketch out this scenario, what you have, label and shade everything that you are given. So what I'm going to first do is I'm going to draw myself a normal curve. I'm going to use the N notation, 155 comma 3. That means the mean and the standard deviation are going to go in that order. We're going to mark the mean on there. You don't need to count all the standard deviations out. I think that's extra work. You're going to label the boundary value, so the 160, and you're going to shade in the direction the problem wants you to shade, so less than 160 feet. So I'm shading over here. Get your sketch. Then you're going to go to your calculator. Now, let me show you how to get all that. So on your calculator, in the same menu that your binomial distributions would be in, you're actually going to go to second vars, and you're going to hit up something called normal CDF. It's right below it's the number 2, and you're going to press enter. Now, the way normal CDF works is the lower bound is whatever the left side of the region is shaded. Normal distributions go on forever, so the left side's actually going to be negative infinity. So we have to be able to represent that in the graph here, and we can't really do that here. So what we do is we mimic negative infinity, and your calculator, if the memory's cleared, might say negative 1e99. So you can leave it like that. If it's not there, you can just say negative 999, or you can type negative 1e99 if you want. But as long as you have a sufficiently low negative number, that'll represent negative infinity. The upper bound will be whatever your boundary value is here. So it's going to be 160. And we're going to set our mean and standard deviation just as we were given. So our mean is actually going to be 155, and our standard deviation is going to be 3. And so you'll get a probability of about 0.9522. So that roughly translates to about 95.2% of this part of the normal curve is shaded. So let's put that in context of the problem. You go to your normal CDF and you're going to write this stuff here. So when you're showing your work on there, your inputs are literally going to be normal CDF, lower bound negative infinity, upper bound 160, mean 155, standard deviation of 3. Don't write paste, obviously. Make sure that you use negative infinity for that and not negative 99999. Then you're going to answer the question. Okay, once you have your value, we have approximately 95.2% of cars of this make and model make an emergency stop in less than 160 feet. The question says, is Dontrell likely to be able to stop the car in less than 160 feet? That's a pretty strong likelihood of that happening. So he most likely will stop the car because 95.2% of the time that car stops. Now let's talk about how to calculate area from a normal distribution. So Kelly Korda was one of the top golfers on the Ladies Professional Golf Association, LPGA Tour in 2022. When Nelly hits her driver, the distance the ball travels can be modeled by a normal distribution with a mean of 274 yards and a standard deviation of 8 yards. A. On a specific hole, Korda would need to hit the ball at least 260 yards to have a clear second shot that avoids a large group of trees. Is she likely to have a clear second shot? Justify your answer. So let's label the things we have. We have the mean, the standard deviation, and at least means greater than. So we want to greater than or equal to, but in this case, just greater than would be fine. We want to label the things. So we're going to sketch out a normal curve. N 274, comma 8. Your boundary in this case is going to be on the low side. So 260 because we're going at least, so greater than or equal to. So 260 will be below the mean. So I'm going to write it over here. I'm going to shade in this direction. Next thing I'm going to do is I'm going to go to normal CDF one more time. So in our inputs in this time, it's going to be a little bit different because we're going to the right. Your lower bound will actually be the value that you were given. So 260 will be here. Your upper bound will be all the way to the right. So that's going to be positive infinity. So to mimic positive infinity, you can do a bunch of nines, 9999, or you can write 1E99 if you can do that in the calculator. Keep your mean and standard deviation from the problem. So actually, this is a different problem. So the mean is going to be 274 while the standard deviation is 8. We'll go down and paste, and you'll get a percentage of about 95.99%. So we'll write those inputs when we're doing the work. What you see here in blue is going to be what you'd want to write. Your lower bound would be 260, your upper bound would be infinity, your mean is 274, and your standard deviation is 8. And write your percentage down or your decimal. Also, make sure you write normal CDF. You have to write the calculation that your calculator is doing. So don't just do lower bound, upper bound, but actually write normal CDF. All right, this question says, is she likely to have a clear second shot? Again, another high probability, so she is likely to have a clear second shot in this case. Part B, on a different hole, Korda can drive the ball onto the green if she hits the ball between 275 and 295 yards. How likely is she to accomplish this goal? This is going to be a similar situation, but we're going between two values this time. So there is no infinity. We have a clear lower bound and a clear upper bound. So we're going to use our normal CDF. We're going to put our lower bound and upper bound as the numbers that are given to us. Keep the same mean and standard deviation. And you're going to get about 44.6% in this case. So the question is, how likely is she to accomplish this goal? Well, I would say she has about a 44.6% chance of making the shot. So make sure you draw your sketch, you write your inputs, and you answer the question. Draw your sketch, write your inputs, answer the question. Now let's talk about how to get percentiles. This case, we're going to work backwards to get them. I'm going to show you two ways to do it. All right, first way is um, you're going to involve the old-fashioned way. We're going to get a, a use the table A, get a z-score, and work backwards. So, according to the U.S. Government Centers for Disease Control, the heights of 3-year-old girls are approximately normally distributed with a mean of 94.5 centimeters and a standard deviation of 4 centimeters. 75% of 3-year-old girls are taller than what height? So we're going to draw our sketch out. We're going to label our mean, but we don't know the value. So we're going to write 94.5, comma, 4, because that's our mean and standard deviation. And we have to make sure we read this carefully. It says 75% of 3-year-old girls are taller than one height. So we have to go to the right. So we're going to figure out, well, I'm going to estimate a number to put a line here. It doesn't really matter how accurate you are, as long as you're on the right side. And then we want to think, all right, I want to shade 75%. But in order to do this correctly, we actually have to go to the left. So we're going to take that 75% and subtract from 1. So 1 minus 0.75 is actually going to be 0.25. What we're really looking at is the 25th percentile. So what we're going to do is go into our table and find the 25th percentile, and that's going to be in the negatives. So we're going to find 0.25 or something as close to it as possible. And that's going to be somewhere right around here. So 0.242, 0.26, 0.248, 0.2514. It looks like it's going to be one of these two here. So the closest one's going to be 0.2514. So we're going to find our z-score. We're going to go out here. And that's going to be negative 0.67. So your z-score is going to be negative 0.67. So now we can work backwards to figure out the value. Remember, the z-score is going to be value minus mean divided by the standard deviation. So now that we have the mean and the standard deviation and the z-score, we can actually find the value. So now I'm going to take my value, or what I'm trying to find, is we're going to take negative 0.67. We're going to set that equal to value. I'm going to call that x. So we'll call this x here. We're going to subtract our mean, and we're going to divide by 4. So take your calculator and solve that for x. Negative 0.67 multiplied by 4, and then plus 94.5 will get you x. See what you get. Using my calculator, I'm getting a value of about 91.8. So let's imagine a different way to do this now. There's definitely an easier way to do it. And that's going to be using one of the calculator features in your VARS menu. So I'm going to clear these drawings here. So the way I would recommend you doing it is sketch your curve. Again, sketch above, so 75%. So we want to subtract that from 1, get 25%. We're looking for the 25th percentile. So this is the function you're going to use. You're going to use inverse norm. So here's how it works. Go to second vars, inverse norm. And the area that you want to put is the area to the left. So we're going to put 0.25, not 0.75. Some of your newer calculators do have a left, center, and right option. But I would encourage you guys to stick to the left because not every calculator has that option. So you want to use the one that works for all of them just in case you don't have yours. So we're going to go to paste and we're going to get this number. Now this number is your z-score, negative 0.67. That's the same number we got from the table. But now we can take that number and solve the same equation we did before. So use your inverse norm. Remember to get the area below. So subtract, if you're going above, subtract that number from 1. Calculate it, and notice that I calculated it as 91.8 without having to do 0 and 1. So let me show you how to do that even easier. So you could get the z-score and plug it into the formula and solve and get 91.8. Or you could do second vars, go to inverse norm, and you could actually make your mean and standard deviation the values that are there, the parameters. So 94.5 is your mean. Your standard deviation is going to be 4. And if you go down and click paste, you will get that exact value, 91.8, and you don't have to solve the equation. So instead of saying negative 0.67 multiplied by 4 plus, what was our mean, 94.5, we got that answer directly. So that 91.8 came from there. And you can show that work by writing your inputs on this. So you would write inverse norm, area below, and the mean and the standard deviation, and then you would get your value. Interpret it if you need to. So in this case, 75% of 3-year-old girls are taller than 91.8 centimeters. All right, here's a check your understanding. This has several parts, so pause the video and I'll go over each part. All right, here's the question. High levels of cholesterol in the blood increase the risk of heart disease. For teenagers, the distribution of blood cholesterol is approximately normal, with a mean of mu 151.6 milligrams of cholesterol per deciliter of blood, and standard deviation of 25 mgs per dl. Part A says cholesterol levels less than 120 milligrams per decimal are considered low for teenagers. About what proportion of teens have low cholesterol levels? And here we go. So we're going to sketch our graph where our boundary is going to be 120. We're going below since it's less than. Do your notation, normal 151.6 comma 25. We're going to go to normal CDF. Our lower bound will be negative infinity because we're going to the left. Upper is 120, mean and standard deviation should be all written, and you want to calculate your value. Double check in your calculator that you can get this number, 0.103. And so then I'm going to do my interpretation. About 10.3% of teenagers have low cholesterol levels. Part B. Again, pause the video, and I'm gonna work it out in 3, 2, 1. Cholesterol levels of 100 milligrams per deciliter or higher are considered high for teenagers. What percentage of teens have high cholesterol? And here we go. So we're shading above in this case. So we're gonna have our lower bound be 200. Our upper bound is gonna be infinity. So notice that our upper is infinity because it's going to the right. Mu and sigma are going to be the same. And you get a small number, and that's about 2.64% of teenagers with high cholesterol levels. Part C, cholesterol levels between 170 and 200 milligrams per deciliter are considered borderline high for teenagers. What proportion of teenagers fall within this category? Now we have two defined boundaries, so there's no infinity. We'll actually put our lower and upper bound in there as is, and you get about 20%, 20.44%. Part D, find the 20th percentile of the distribution of blood cholesterol. So in this case here, the percentile is at or below. So we want to use inverse norm. For the area to the left, you'll use 0.20. We don't subtract from 1 in this case because inverse norm by default goes below. And then the interpretation is a cholesterol level of 130.6 milligrams per deciliter is at the 20th percentile for teenagers. And finally, part E. 25% of teenagers have blood cholesterol higher than how many milligrams per deciliter? So this is a higher than problem. So we're gonna want to subtract that from 1, put that number in the inverse norm, and you'll get 168.46. So the interpretation would be 25% of teenagers have cholesterol levels higher than 168.5 milligrams per deciliter. That's also the third quartile, by the way. All right, in this example, and this is our last example, we're going to talk about how to get the mean or the standard deviation. So we've been able to get values, we've been able to get percentages, but we haven't been able to solve for the mean or standard deviation. So these are the ones that are going to involve a little bit more work, but not too much. So letter A, according to the study by Rescue Time, people spend an average of 1.25 minutes on their smartphone each time they pick it up. If Noel's distribution of smartphone use is approximately normal with a mean of 1.25 minutes and a 97th percentile of 2 minutes, calculate its standard deviation. So in this problem, let's identify some things we have. We have the mean, 1.25. We have the percentile, so that's the area to the left, so that's 0.97. And we have a value of 2 minutes. So in this case, we want to get the z-score. So when we're trying to get a mean or standard deviation, we're going to have to settle for getting the z-score first. Now remember that the standard normal distribution has a mean of 0 and a standard deviation of 1. So to get the z-score without using table A, you're going to go into inverse norm. You're going to put your percentile or the area to the left, but you're going to leave the mean at 0 and the standard deviation as 1 and keep that tail going to the left. So you're going to get a z-score of about 1.88 in this problem. Now what you're going to do with that number is you're going to set it up in the z-score formula. So remember the z-score formula is value minus mean divided by standard deviation. So we know the z-score, we know the value, we know the mean. What we don't know is the standard deviation. So we'll plug the three things we have and solve for the standard deviation. In this case here, it would make sense to move the standard deviation up and divide by the 1.88. So you can swap these out if you want in these type of situations. Do that calculation, 2 minus 1.25, and divide that number by 1.88, and you will have your standard deviation, which is about 0.399 minutes. You can always check your work if you want. Easy way to check it is if you go to second vars, inverse norm, and we'll put 0.097, and we're going to go ahead and put our mean and our standard deviation that we just found in it. So the mean in this case is going to be 1.25, and our standard deviation we just got was 0.399. We'll keep it left, and notice that that gives you 2. That's your value, and that's the value we were provided from at the beginning. So that checks. So we did our work right. You try letter B. For young adults, the distribution of blood cholesterol is approximately normal with the mean of 157.5 milligrams of cholesterol per deciliter. About 8.9% of young adults have high cholesterol, that is, levels of 200 milligrams per deciliter or greater. Find the standard deviation of the distribution of blood cholesterol for young adults. So you might want to pause this and give it a try on your own. We're going to go over it in 3, 2, 1. So here we go. Let's identify some key points. We're given a greater than, so we're given an above. And we like to go below in the z-score formula. So make sure you take your percentage and you subtract it from 1. So 0.089 is the decimal. Subtract that from 1 and you get 0.911. That's going to be your left area. You're given the mean, you're given the value. We need to find the standard deviation. So now we can go to inverse norm. We can plug in our inputs. So we'll write inverse norm, area left, 0.911, mean of 0, standard deviation of 1. You get a z-score of 1.347. You can go to 2 places if you want. I'm going to use 3 in this case. We'll plug it into our z-score formula. solve it for the standard deviation. Use your calculator, and you get a value of about 31.55 milligrams per deciliter. All right, one more part. A tennis ball machine fires balls a distance that is approximately normal distributed. The mean distance, mu, is unknown, and the standard deviation is 1.2 feet. If 5% of the balls go farther than 70 feet, find mu. So we have 5% of the balls go farther. Again, this is an above problem. We want to go below, which means 95% of the balls will go below. So subtract that number from 1. You have your standard deviation in this case. We don't have the mean. We have our value. So we'll get our z-score, area left, 0.95, mu 0, sigma 1. You get a z-score of 1.645. If you plug it into this formula here, our variable we're solving for is actually in this spot. It's going to be a little bit trickier than solving for the standard deviation because we have to get this up here and move everything over. But multiply that 1.2 to the 1.645. And then what you can do is you can move the mu over here and subtract this 1.645 times 1.2 from the 70. And you can do all that operation right in your calculator from there if you'd like. So you should get a mean of 68.03 feet. Of course, I'm going to check that. So I'm going to check that again using inverse norm. And I'm going to use 0.95. I'm going to make my mu the number that I just calculated, so 68.03. And my standard deviation was given to me at 1.2. If we did this right, we should get about 70 here, which should match our 70 feet here. So everything's good. That concludes our lesson for today. I hope this was helpful. This is one of the most fundamental things in this class, so it's very important that you know how to utilize the normal distribution because it's going to be used in so many other things. Thanks for watching. I hope you find this helpful.